depends upon some other factors. That is this force enough to overcome the maximum static friction that's basically pushing back on this.
What if the kinetic friction is also greater than 0?
I mean, that still holds. Because if you look at the forces acting on that mass there, we got tension acting this way, we have static friction this way, weight, and a pathetic marker, and a normal force. The maximum static, Fs max, is the static coefficient times the normal force. That normal force for that top block would just be its weight, since I have only two vertical forces there. So that's mu s mg. So I have tension minus my static friction is equal to the mass of that top block there, m sub t, times its acceleration. Meanwhile, for the hanging mass, you have mass of the hanging mass minus the tension is equal to hanging mass times A. Then those accelerations will be the same, and then we've also got F of S acting on the 10 kilogram mass is equal to mass bottom times A. Bottom. So the question is, are these A's the same?
Well, there's no force holding the 10 that way. So
Yeah.
why wouldn't they be the same?
Why wouldn't the accelerations be the same?
Yeah, that's what I don't understand.
Think about the tablecloth trick. You got tablecloth, dishes on top of it. If you yank the tablecloth hard enough, the dishes don't come with it. If you do it slowly, the dishes will come with it.
Okay.
So if that top mass is pulled fast enough or hard enough, if the force applied to it is great enough, then it'll move this way, will overcome static friction, and then kinetic friction's involved. So the top block would accelerate at a greater rate than the bottom block. But they will both move.
But if it's just done slowly, then they both move at the same rate?
Yeah.
How would you be able to calculate how fast?
I see. So the question is, how fast would it have to go for it to not bring the other box with it?
Or like,
Yeah, or
how
what
fast do you have to move the box at the end of the pulley in order for the two boxes to move as a unit?
I
So
guess it's
you
more about-
would, if all the accelerations are the same, and we're at maximum static, then
That's a whole other, what is this?
there might be something missing here. Let's hold this off, considering it's 2:52, for another time, or during the break, let me take another look at it.
Thank you.
Other questions?
Question though.
All right. Let's take a look at a couple of problems as we work our way towards the next chapter. Infinitely long wire with some current I. Let's make this 0.03 meters, we'll make that 0.05 meters, and that 0.06 meters. And what I wanna know is, this is a wire here. What I wanna know is, what is the magnetic flux through the middle of this wire? There's no current running through this. The current's coming from here, creating a magnetic field, which is gonna be going through that.
What? Okay.
So really long wire and then just a square of wire sitting above it.
Okay.
That's not a cross section of the
No,
wire?
it's not a cross
That's the
section,
whole
it's,
wire.
I have a wire that's been connected to itself and put into a shape of a square or a rectangle.
Okay.
It's a calculus problem. All right, I know that the magnetic field coming from this, or the magnitude is equal to mu naught times I over 2 pi r, where r would be the distance from the wire to some point in question. I know magnetic flux is equal to V dot dA.
Okay.
I know the magnetic field's not constant through here, and we deal with a lot of problems where it's constant, but the magnetic field's not constant because, well, the farther away you go, the weaker the magnetic field.
Oh, that's the calculus problem, okay.
Yeah. And also note, I don't have a circle in the integral symbol because it's not a closed surface, it's just it's an open surface.
Okay.
So, my magnetic flux, integral of B dot dA, well, I have a formula for B, that's mu naught I over 2 pi r dA. Now let's deal with the dot product aspect of it. Which way is the magnetic field going through this surface?
That's a good question.
I thought so.
Current's going this way.
Yep, current's going that way.
Is the magnetic field, does it go the same way with current?
It's negative J.
All right, let's set up a coordinate system so we can communicate more easily. I hat to the right, J hat up, and K hat coming at us.
So our current's going in the positive I hat direction.
Correct?
And then cross it with the oh, no, that's an external magnetic field.
Doesn't it depend on where you're at though?
Anywhere inside here.
It's perpendicular with the current, right, magnetic field?
Yep, it would be.
So it's a positive J hat, or?
Nope.
When you go negative K hat?
How'd you get, all right, so first off, how'd you get positive J hat and how'd you get negative K hat?
Positive J hat just because I is going this way, J is going that way, I don't know.
If the current's going this way, I was using my left hand.
Yeah, there you go.
Doing I by J, so you get K hat.
You are not the only one who's ever done that.
Because I'm pretty sure your direction's right.
Yeah, it's not the dominant hand and it's not the free hand, it's the right hand.
Alright, yeah, that makes a little more sense.
Okay, therefore,
Okay, so it would be coming positive K hat.
yes.
Alright.
Thumb points in that direction, the right hand rule. Above here, it's coming out, below it's going in front of it's going down, and in the other room it's going up.
I see what you're
Going in that direction.
So positive K hat is coming at you.
Yep. So up here is positive K hat, down here, negative K hat,
Yeah.
in front of it, negative J hat, behind it, positive J hat.
Okay.
Yeah, thank you.
So I'm gonna make my area vector, because again, area vector is perpendicular to the surface, and whichever direction I like, I'm gonna make it that way. So my dot product is just B times A. So in this case, or BDA. So it's a simple calculus problem here, except I have a variable here of R and I have a variable here of A, and I need to get them together. What is the formula for the area
length times width,
Pardon? Okay,
the 0.06 times 0.05.
that would be the total area. I need to get down to DA. That's not cool, but so much easier, but, all right, let's do it this way. I know that the magnetic field at this point would be the same actually everywhere along here. Because this wire is infinitely long, there's no reason for the current to be different here, or here, or here, or sorry, magnetic field to be different anywhere along that line. So DA is the area of this infinitesimally thin line right here. Whichever one, call that one length, we call that one width. So this becomes the integral of mu naught I, actually those are constants, let's go ahead and pull them out. U naught I over 2 pi, 1 over r times the length times the thickness.
Why wouldn't the magnetic field strength vary depending on where it's at?
Oh, depends, it varies depending on where you are this way, it doesn't depend upon where you are this way.
But
So you're saying that the area is gonna be different depending on your value of R? And that's
I'm
why,
saying that B is different depending upon the value of r.
then if we plug that in for B, oh, no, but the radius, okay, never mind.
I get what you're saying.
We pulled that out. Okay.
Yep.
Alright.
so because that, we're considered, we're assuming that L is constant, because
Yeah,
wherever you are, so that's why, so we could take that out and now it's only in terms of R.
yep,
Okay.
Okay, that makes more sense.
So,
we also have a single variable here, so I can do now my limits of integration. What are the limits of integration?
From 0.03 to 0.08?
I think it's 0.06, right? Or no?
nah.
All right, the smallest r can be is 0.03, the largest is 0.08.
Yeah, or length.
Times length,
Oh, okay.
length's already here.
Oh, I see.
So I got u naught I
That makes sense.
length over 2 pi times the integral of 1 over r dr from 0.03 to 0.08. Got a calculus problem here?
You can do that on a calculator.
Can, but
You would prefer not to do that,
Is it-
because it's physical.
I don't know,
LNR.
it's
All right,
not,
do you
it's
not-
not technically wrong if you do that. I don't know how, the calculator's gonna be
Yeah,
doing
I
it
think
through,
Natural log of,
doing a bunch of tiny rectangles.
yeah, it is.
I assume. It's gonna use one of the
Wait for it.
approximation
I'm
techniques.
not sure how it's programmed to do it, I just know that you can do it.
Well, the integral's LNR.
Yeah. So this is mu naught I L over 2 pi, over 2 pi times the natural log of r from 0.03 to 0.08. And so this becomes, that is 2 times 10 to the negative 7th. I didn't give a number. Let's make it 3 amps. That's 3 L 0.06 times the natural log of 8/3. And that's gonna be some number.
Wait, why is it 8/3?
Because when you subtract natural logs, you can divide them like that.
Well, yeah, but it's 0.08. Should it be 0.08 divided by 0.03?
If you want.
Sorry, Dr. Fox?
0.08 divided by 0.03 is the same as 8
The
divided by
Yeah, it'll
decimals
still be the
still be the same.
For the, on the right, you simplified the
I don't know that.
mu sub naught, right? That's why it's 2 to the.
Yeah.
Okay.
U sub naught divided by 2 pi is 2 times 10 to the negative 7.
Okay, so ln 8 minus ln 3 is the same as saying the natural log of 8/3.
Yes.
Okay. How about that one?
And when you add them, you multiply them, right?
Yes.
Okay.
Thus the Noah's Ark logarithm joke.
Wait, what?
What?
when I taught Algebra 2 trig or Algebra 3, I always wait to get to the log section just so that I was, could do this one joke. Students presumably laughed on the inside.
I like jokes.
So after the ark finds land and the animals go forth, then they're told to go forth and multiply. And, you know, a year later, Noah's going around checking all the animals, and rabbits, there's now 50 rabbits, and there's, you know, I guess elephants still in gestation. But he keeps going around and he finds these 2 snakes, and just 2 of them. And there should have been more. He said, why haven't you gone forth and multiplied? And the 2 snakes said, we can't, we're adders. So, year later, there's a second punchline coming up. Year later, Noah's going around, and now there's 5,000 rabbits, and there's several elephants and so forth. He comes across the 2 snakes, and there's a bunch of little snakes going around. And he said, I thought you were adders and you couldn't multiply. And they said, well, we use logarithms.
I don't get it, what is it,
Like
adder?
adder instead of multiple, like the,
Adder is this type of snake.
Oh, is it, okay. Now I understand.
I was first told that joke when I was probably about 10 years old. No idea what it meant.
It says for
My cousin.
solid.
Good one.
There must have been.
All right.
That reminded me of something.
Yes.
So in high school, our math teacher told us to come up with the best math pickup line, and I ended up winning with, "Are you the greatest common factor? Because I'm about to take you out."
The greatest corny one.
If there is no pause.
There was,
It was the only one that was actually somewhat funny.
I thought that was good.
there were,
Jess is gonna use
Dude,
it.
I'm dead ass gonna use it now. Next person I see.
It's funny because I told my girlfriend at the time that, and then she ended up using it and won.
there was, look, in grad school, they had weekly seminars, which somebody would be presenting with the material, and there were a group of us who would get together and come up with top 10 lists that we would somewhat secretly post on the door next to it. And one of them was the top 10 pickup lines by physicists. So at some point, if I find it, I will share them.
Resources remaining.
The one that I remember off the top of my head was, I know all the Greek letters.
Good one.
You'll get all the Greek girls.
All right. Questions about this problem?
The unit is Weber?
Yes, it would be Weber's. Or Tesla meter squared, if you're feeling that way. All right, so let's do a little problem that's gonna bring back some fond memories from 251. Or memories, not fond. I have an incline here. So side view looks like that. Overhead view, I got 2 wires here, so if I try to come up with an attempt, basically I got these two incline wires like that, and there's a wire that runs across it. I'm gonna call this point P, call that point Q. So there's a wire that's running perpendicular to the board, or from an overhead view, across like that.
But there's 2 wires right
Yeah.
next to each other like that, okay.
Or it doesn't incline, sorry, I was thinking of a different problem. These 2 don't have to be wires, but they do have a wire running across like that, and there's some current flowing through it.
Okay, so there's just one wire coming down and a wire over it like that.
Think like Golden Gate Bridge. How there's 2, you know what I'm talking about?
I
There's
know
like
what the Golden
2
Gate Bridge is, but
Yeah, there's like there's 2 sides and then there's usually stuff that like goes over it.
So there are 2 wires on the sides.
I misspoke, let's start over again. I have 2 incline, actually, it could just be an incline plane. Let's simplify it, because the picture I have in my head is different than what I'm about to say, but it does not affect it. I have an inclined plane here. Inclined plane.
Okay. Oh, it's like a three-dimensional incline plane, there you go.
Or from a side view, it looks like that.
So there is two.
I've got a wire that's sitting on top of it. So I've got this inclined plane with a wire sitting on top of it. That wire is it's frictionless, so that wire is free to move up and down. Well, actually, if I just put it there, it's free to move down. I have a magnetic field going up. Oop. I have a magnetic field coming up, so from this point of view, it would be coming out at us, or from here, it's sort of moving in that direction. Oop, that is bad.
I get what you mean.
It's going straight up. So if I set it up into a I hat, J hat, K hat, from this point of view right here, my magnetic field is B J hat. So inclined plane, wire across it, magnetic field going straight up. My magnetic field let's be more specific here, let's say 5 Tesla J hat. This wire has a mass of 0.3 kilograms. The distance from here to here, or this distance, is 0.1 meters.
Which wire has a mass of 0.3?
So there's actually only one wire. It's one that's gonna slide down.
Oh.
The question is, what current runs through the wire such that the wire